So we were looking at what happens when you try to invent a stellar model using general relativity as opposed to Newtonian physics. And we had got the external metric. So this is the metric outside the star. Which we knew to be the Schwarzschild metric because stars are spherically symmetric and static. Let's make that a capital M. The metric inside the star we said was going to be similar, but perhaps strangely parameterized, so that this was minus e to the 2 phi of r dt squared plus dr squared over 1 minus 2 m of r divided by r plus r squared d omega 2 squared. And obviously the whole solution has got to match up at the surface. The surface of the star is at r equals big R. So that's our starting point, and the energy momentum tensor for this object we said was going to be TAB, which is P plus rho into UA UB plus P times GAB, the usual way of parameterizing material with pressure P and energy density rho. And we had got the velocity 4 vector UA, it's normalized to minus 1, so UA with its indices upstairs is e to the minus capital phi, e to the minus capital phi, 0, 0, 0. So that means UA with its indices downstairs is minus e to the plus phi. Now what you do, you simply have to solve the Einstein equations for this situation. But there are... What happened to the light here? I have a feeling that this controls all... Yes, all at once. I guess it's dead. Never mind. So, a step in solving the Einstein equations that makes life easy is to first of all look at the conservation of the energy momentum tensor. Well, the only reason that I've done that is that the only component of u which is non-vanishing is the time component. You don't want to have any motion in the spatial directions, so the spatial components will be 0. So the only component that you can have is a time component. Let's call it x. Whatever x is, UA with its indices downstairs, you see, will be equal to x e to the 2 phi with a minus sign in front of it, because the only time component of the metric is the minus e to the 2 phi that we have there. So that must be what it is downstairs. And lastly, because you know that UA has got to be equal to minus 1, so that the thing is properly normalized for a velocity, that tells you UA equals minus 1 implies that x squared e to the 2 phi, that times that, is equal to 1. So x is e to the minus phi. You might conceivably have chosen x to be minus e to the minus phi, but that would be perverse in the extreme, because this thing is the time component of something, and if you think that the thing is moving forwards in time, you usually choose that to be positive. So, because this would represent, for example, dt by d proper time, so that thing had better be positive. Is that the answer to the question? So you just substitute in, first of all, the energy momentum tensor. Let's do that. You get del A of, from over here, P plus rho UA UB. Then you get plus del A of P times GAB. And I think the easiest way of writing that is just to say that this is equal to... Actually, I'm going to lower the B, in which case this becomes del B of P. So we end up with that. And now you just write out what you've got. The first term looks like UB, UA, del A of P plus rho when the derivative acts on that. Then there will be a PA plus rho UB del A of UA when the derivative acts on the first velocity term. Then there will be a term that looks like P plus rho into UA del A UB, and lastly there will be a del B of P. And that's all got to be equal to 0. Now you have to simplify this a little bit. It's not terribly hard. The only component of this which does not vanish is the 0 component. But if you think about that, that means that this is a scalar. U0 D0 means that has to be the time derivative, and we know that the situation is static, and therefore this term gives you absolutely nothing. Then you can stare at this term. It is, of course, tempting to say, oh, well, of course, the same thing is true, but you have to take an extra step to see that it really is true. The easiest thing to do is to rewrite this as P plus rho, UB, and then adopt, you see there's a connection term sitting in here, so you don't really know that the connection term gives you nothing. But there's a sneaky way of writing the divergence of any vector as determinant of g to the minus a half, dA partial, determinant of g to the plus a half times UA. I presume you've all seen that trick before. No? Yes, good. Then there is this term 2. That 2 looks like it ought to be 0 because here you have U0 del 0, but still there is a connection term in there, and so it is not obvious that you really do get 0. So if you write out explicitly what you've got UA partial dA UB. Then there will be the connection term, which is minus P plus rho UA gamma A B C U C, and then you end up with dB of P. And that's got to be equal to 0. Now you can simplify things using the same reasoning as before. This term must be 0 because the only component here is 0. That means that this is d by d0. Nothing is time dependent, so you get nothing for the same reason that you have over there. Also here you get nothing because this is U0 D0. It's the only non-vanishing term in this combination of stuff. Such reasoning does not work on this term so directly, and neither does it work on that term. So this whole expression now collapses down because the thing is static to del B dB of the pressure is equal to P plus rho UA gamma C A B U C. There are, on the face of it, 4 equations there, Again, there's a little bit of simplification you can make, because again, here the only component is a 0, and here the only component is a 0. So you can say that this is really dB of P equals P plus rho U0 upstairs, gamma with a 0 there. This is a 0, so that's got to be a 0 and then a B. And since you know what U0 is, this turns out to be P plus rho gamma 0, 0, B with an overall minus sign. So that's as much as you can get easily from the equation of energy momentum conservation. To go further, you've got to evaluate this Christoffel symbol. That's kind of easy. Gamma 0, 0 anything is equal to a half of G0, 0. It's got to be that the only inverse component of the metric you see will be 0, 0, the only one that has a 0 in it. That's because this metric is diagonal, so it's an easy calculation to invert the metric. Then there will be a minus D0 of G0B, plus a D0 of G0B, plus a dB of G00. So that cancels that, even though it's 0, both of them, and you're left with this term. Now you can use the fact that everything is spherically symmetric, so the only interesting component of this equation is going to be the radial component. So gamma 0, 0 R is equal to a half of G0, 0 upstairs. That's minus e to the minus 2 phi. Then there is a dr of G0, 0 downstairs. That's d by dr of minus e to the plus 2 phi. So you collect up all the terms and you will end up with this term cancels that. All these minus signs go away. Taking the derivative cancels this 2, and you're left with d phi by dr. Deceptively simple. So the resultant expression is dp dr. Let's write this over here. Is equal to P plus rho with a minus sign times d phi dr. That equation ought to look fairly familiar to you. Had you been doing Newtonian physics, you would have got the same thing for a Newtonian star. If you think about just looking at hydrostatic equilibrium in a gravitational field, you would get dp dr is equal to minus the density times g. But g is just d phi dr. So this is basically the same thing as a Newtonian equation, with phi being the Newtonian potential. And the only difference is that you end up with an extra pressure term here. That's absolutely normal for general relativity. Often, when you compare a general relativistic formula to a Newtonian formula, you find that where you have the energy density, you end up with pressure plus energy density, or perhaps 3 times pressure plus the energy density, as you do in cosmological models. So this is very, very similar to what you get in Newtonian physics. Where phi would be the Newtonian gravitational potential, So you can regard the pressure term as being a relativistic correction to what you get from Newtonian physics. Now you can see why it was that I chose to parameterize my metric in this way. I chose an e to the 2 phi here. I could have chosen some other way of writing the metric, but I chose it deliberately that way so that I'd end up with this thing as looking like the Newtonian potential. That often works, but is not absolutely universal. So that's why I did things that particular way. To get further, you will need to look at the Ricci tensor and hence the Einstein equations. It's often worth your while going as far as you can without solving the Einstein equations. That is as far as you can possibly go. Now, I could stand here and calculate the Ricci tensor from this if you wanted me to, but I'm sure you would not enjoy that. I certainly wouldn't enjoy the experience. So I will tell you what you will get. The 0, equation turns out to be 2 over r squared d m of r by dr equals 8 pi times the energy density rho. The RR component is 2 over r into 1 minus 2m of r over r times d phi dr minus 2m of r over r cubed is equal to 8 pi times the pressure. I do not expect anybody to remember this formula. So, this is complicated. This is relatively simple. You could say, well, what about the other 8 Einstein equations? They give you nothing interesting or new. So we have a beautiful looking expression that looks like that. If you stare at the top equation, the 0, equation, you will see that there is in fact something nice about it. Let me rewrite it. I can rewrite that expression as m of r is the integral of 4 pi r squared rho. Rho in general will be some function of r, so it looks like that. Now let's just think about what that actually means. This, of course, would be a familiar expression because it looks like it's trying to say m looks like a mass, and this is the integral of the energy density over a region inside some sphere. So if you imagine that you've got the star that looks like this, here is the center, then what you're doing is you're constructing little shells that look like this. Rho is a function of r here, and this expression reflects that fact. So you can use this with a little bit of physics to make your life easy. You really want to say this is the integral from 0 to r. M of 0 the mass enclosed by the origin, which is nothing, ought to be nothing. So this now represents the total energy enclosed inside a sphere of radius r. That is why I decided to use this form of the metric. I could have written this in many different ways. I could have said it was e to the 2 nu times r, which is what often seems to happen in books. But then I wouldn't have this nice picture of what was going on. I wouldn't have a nice picture of the mass. So the fact that I wrote it this way is what gives me a nice interpretation. So this is a sort of natural thing to do. Lastly, there is the remaining Einstein equation, and I know of nothing nice you can do with that. You just have to write it down. The best that you can do to make it look nice is to get rid of the phi dr term from the conservation of energy momentum. So you want to get rid of the phi dr term here and just write things in terms of the pressure, in which case you will end up with this is dp dr equals minus into p plus rho. Then an 8 pi p plus 2m over r cubed, this is m of r, remember, divided by r squared over 2 into r minus 2m. And if you like, you can rewrite this in a slightly more benign form, minus p plus rho, using the mass function equation over r into r minus 2m, which is still a function of r, remember, into m of r plus 4 pi p r cubed. That is as good as you will get. This is sometimes called the Oppenheimer-Volkoff equation. After the first people who studied this in this context. So that's what you get when you try to build a relativistic model of the star. To go further, you will need to find an equation of state that you can use to describe the matter of the star. So it's kind of obvious that you need to do this. You've got the pressure here and the energy density. Of course, in realistic substances, the pressure is related to the energy density. You know one, you know the other. This thing is P, this thing is rho. Such a relation is usually called the equation of state. And there are many equations of state for realistic matter on the market. You will have to adapt your equation of state to whatever the true physics of the situation actually is. However, we can do one calculation analytically. Most of them will make you resort to the use of computers, I'm afraid. I don't want to do that. using a computer will give you the same qualitative picture as the one we can get from a simple analytic treatment of something. So, we think we're going to be interested in very dense stars, like neutron stars. A typical neutron star is a few kilometers across and contains the mass of, roughly speaking, the Sun. It can be thought of as being composed of degenerate nuclear matter, and to a first approximation, the equation of state of such things is energy density equals a constant. And the pressure is whatever you like. Another way of saying that is that nuclear matter is absolutely incompressible. Such a thing is not actually possible, because if you think about it, something which is incompressible will have speed of sound equal to the speed of light. That doesn't seem to make any sense, but this will do as a first approximation, and it leads to something which you can solve. So that is going to be my equation of state. That means that I can now integrate everything up. And in particular, I can start off by integrating up m of r. If rho is a constant equal to rho 0, m of r is equal to 4 pi over 3 r cubed rho 0 for r less than big R. And it means the total mass, big M, that's the value, well, this is r equals r. There is nothing outside r equals r, the surface of the star. So big M is equal to 4 pi over 3 rho naught big R cubed. And then, fortunately, this metric coefficient will match up with that metric coefficient at r equals r. Now you just have to integrate up the pressure. We know m of r, so we can substitute it into here. And here, we know rho, and you can substitute into there. And so you end up with a first order differential equation which you can integrate. If you do that, I will warn you, it is a bit of a struggle. So it's one of these things that you enjoy doing over a cup of tea. You will discover the pressure as a function of radius is equal to rho naught. And then a big bracket, 1 minus 2mr squared over r cubed, where this m means capital M to the 1/2. Minus 1 minus 2m over r to the 1/2 for divided by 3 into 1 minus 2m over r to the 1/2 minus 1 minus 2m r squared over r cubed, also to the 1/2. This has the property that you might expect, that at little r equals big R, the surface of the star the pressure is equal to 0. That's because that term will cancel that term. Now, of course, you can see that this must be a rather unpleasant calculation, which is why I'm not going to try to do it in real time on a blackboard. What about the Newtonian potential? Well, e to the phi, you can, of course, calculate from the Einstein equation if you really wanted to do that. You will get 3/2 into 1 minus 2m over r to the 1/2 minus 1/2 of 1 minus 2m r squared over big R to the 1/2 for little r less than r. And you will notice that e to the phi is 1 minus 2m over r to the half as you would expect at r is equal to big R. So again, the time component of the metric matches up smoothly. Sorry? What have I done wrong? R cubed. Oh yes, absolutely right. Thank you. So, the time component and the radial components of the metric match up smoothly at the boundary. Now, what comes out of this analysis as far as physics is concerned? Well, in Newtonian physics, there is no reason why you can't build a star of arbitrarily large mass. General relativity is different. The way to see that is to come back to this pressure equation. If you stare at this equation, you will notice that there is the potential for this term here to vanish, telling you the pressure has become infinite. How can that possibly happen? And the answer is, of course, it can't. This expression must be positive everywhere. Otherwise, the pressure blows up, or even worse, can become negative. So the pressure at the center is the easiest thing to look at. That's the center of the star. There you will see that the denominator looks like 3 into 1 minus 2m over r to the 1/2 minus 1. This had better not be equal to 0. And you can see, of course, it is equal to 0 if this is true. So that would mean that it vanishes. What does that mean? Well, let's put things back into Sensible language, I think the thing to do is to square this. It reads 9 minus 18m over r equals 1. In other words, 18m over r is equal to 8, and therefore r is equal to 18 over 8 sounds to me like 9 over 4. You can't build a star in a given size which has more than that. So this is a bound on a sensible model. So you'll notice that this star, in the most extreme form, is only slightly bigger than its own Schwarzschild radius. But of course you can calculate the mass of this star if you know the density, because you know that m is 4/3 pi rho naught r cubed. So you now have an equation for r. It reads r squared is equal to, I'm going to do this calculation, it's 3, I thought I got it written down here, but I don't seem to have done. One over 3 pi rho naught. Is that right? Okay. And correspondingly, the mass is equal to, well, it's 9/4 of the, sorry, it's 4/9 of the square root of this. So this is the maximum mass that you can have. So for our toy model, let's try to evaluate that in terms of some numbers. Let's see. Nuclear matter, meaning the density of a nucleon, well, that's the mass of a nucleon divided by the volume of a nucleon. Everybody knows that this is roughly 5 times 10 to the 14 grams per cc. What is the corresponding value of R? The answer turns out to be 15 kilometers. The corresponding value of M turns out to be 6 times 10 to the 33 grams, or in units that are more astrophysical in nature, 3 solar masses. So the crudest possible model tells you that you cannot possibly have a neutron star of mass greater than 3 solar masses. Now, of course, the trouble is that in the real universe there are stars with masses greater than 3 solar masses. They obviously can't end up their lives as neutron stars, so what happens to them? The answer is that they will, of course, turn into black holes. And I suppose the next thing that we ought to do is to see how that can happen. Now, you could argue that I've made some kind of horrible, non-realistic assumptions here, because I've just simply said, well, the density is fixed, and the pressure can be anything you like. Anybody's attempts to produce more realistic models have resulted in more or less the same results. The most modern results seem to indicate, but you have to do horrible calculations to do this, So this really comes from realistic equations of state, will give you answers between 1.3 and 2.2 solar masses as the maximum. The uncertainty here arises because in order to understand where you are in this picture, your equation of state has got to be calculated using QCD and nuclear physics in some horrible combination in precisely a regime where you understand very little. That leads to great uncertainties. The reason is that this density is very close to the quark-hadron phase transition, which means actually doing the calculations is amazingly difficult, and perturbation theory is not very reliable. You have to use lattice calculations to get anything real. And that's basically too horrible, hence this uncertainty. But either way, there is a maximum mass. You cannot have stable objects with a mass greater than something like that.
We should also have more than 2m, right?
Sorry?
We also get in trouble with our denominator if the mass is less than, or if the radius is less than
2m? Can't be. Oh, that would be even worse.
So it's between 2m and 2.25 m. Right?
You'd be in terrible trouble, yes.
Yeah.
No, you can't have that.
That's your, yeah.
This is the cutoff. It's easy to see, you see.
Yeah.
So, what you learn is you can't possibly have a static object that is spherically symmetric and looks like a star. So, you ask yourself, what happens? Well, the answer is that if you try to build something that has huge mass inside a given region, it's obviously got to be time dependent. You're not going to get rid of spherical symmetry unless you add angular momentum to it. So what we need to do is look at some time-dependent solutions of the Einstein equations under similar conditions. So let's try that. A moment's thought will reveal this is not going to be easy. That's because whatever I do will depend on two variables, r and t. So I'm going to give you a very simplified one that I can do analytically to give you the flavor of what's going on. Again, a huge amount of effort has been expended on computer models of this kind of situation. So what happens? Somebody gives you a star that looks like that at some instant, and it has mass greater than this thing, so you know you can't have something that is static. What is going to happen? Well, inside there must be some time-dependent metric but outside, there has to be just the Schwarzschild metric, because you have a vacuum solution. For the case of the Schwarzschild metric, we proved early on that spherically symmetric implied static as a consequence of the vacuum Einstein equations. That has got to not work inside here. And I'm going to make a big cheat, and I'm going to make some assumption about the kind of matter that you have here. So I'm going to model the matter inside the star as dust. You can argue this is not realistic. Dust is a technical term for pressure-free matter. And that, of course, is quite different to what we had over there. The reason I have done this is to make life easy for us. If you want to do anything else, you will have to use a computer. If you look on the internet, you can find people who have made movies of collapsing realistic things. Unfortunately, I do not have the technology to play these movies here. Otherwise, we could try. So, inside this dust cloud, you have energy density times UA, UB as being the energy momentum tensor. That's because the pressure is equal to 0. Conservation of energy momentum then tells you that, well, del A of, let's see, how do I do it? Rho UA UB is equal to 0. This is the same thing as UB del A of rho UA plus rho UA del A of UB. This equation here, local energy conservation tells you that must be equal to 0. This is the equation of continuity. Therefore, this thing must be equal to 0. That tells you that the velocity 4 vector of whatever is making up this dust in the interior must move along geodesics. So the velocity 4 vector of the interior matter that makes life very easy for you. Because let's look at this situation. What is going to happen? Well, since gravity is attractive, if you start off with that as an initial state, a little bit later, it will have shrunk because gravity is attractive. And therefore, even later, it will have shrunk to something like that. Let's consider what happens to a particle sitting at the surface. It will follow a geodesic. Now, let's suppose that we have been sensible. This metric inside is going to match up with the metric outside in a smooth way. You know that this particle is going to follow a geodesic, so you have a choice as to whether or not to compute the trajectory of this geodesic in the Schwarzschild metric or the interior metric, and the answer is it does not matter which you do. So for the surface, it is much easier to say particles on the surface follow geodesics in the Schwarzschild metric. Now, if you think about that, that makes your calculation really pretty simple. You know how to calculate geodesics in the Schwarzschild metric. We just did that. So, we will have to do it again. No harm in that. And then figure out what goes on inside here. So the basic point is that because this follows a geodesic, you know what is happening to this surface. So this determines what happens to the surface of the collapsing body. So we should probably stop there because we seem to be out of time. If you like, you can spend the weekend trying to figure out what these geodesics actually are. Okay, let's stop there.
Can I ask a quick question?
Yeah.
How can the spot geometrically static if the boundary is moving?
Just the exterior.
So I suppose so is it the metric static, but the space-time is actually describing?
Yeah, there's bits of it which is time dependent, but you know outside it can't be, because it obeys the vacuum Einstein equations. It's a neat trick.